In this video, we are going to be learning about solutions and about some of the vocabulary around solutions. Specifically, our learning goals are to be able to define solution, solute, saturated solution, solubility, solvent, and unsaturated solution by the end of this video. Fortunately, these terms relate to each other very logically. We're also going to describe the impact of temperature on the solubility of solids and gases in water, and the impact of pressure on solubility of gases in water. Finally, we're going to use a solubility curve, for example, the one on table G, to identify trends in solubility for specific solutes and to determine the amount of a solute needed for a saturated solution at a given temperature. I strongly suggest that you take a moment to make a sketch in your notebook so that you can label your diagram with some vocabulary terms. It's much easier to remember some of these terms if you've got a visual to map them to. So when we're talking about a solution, the terms solvent and solute, pretty important. A solvent is the substance that is doing the dissolving. So if we're thinking about a cup of water and a teaspoon of salt, the solvent would be the water, the substance that will do the dissolving. The solute is the substance that will be dissolved, the substance that is being dissolved. These two words are very similar, kind of just have to remember the difference. Solvent does the dissolving, solute is the substance that is being dissolved. Now, once I take the solute and I put it into the solvent and it dissolves, I now have a solution. A solution is a mixture containing a solute dissolved into a solvent. So our example in this case would be aqueous sodium chloride, or NaClAq. Whenever you see the sign AQ, that means you are looking at a substance that's dissolved in water, or you're looking at a solution. Now, there are two types of solutions that we want to think about. There are solutions that are what's called unsaturated and solutions that are saturated. It's actually a pretty simple difference between the two, and it's a difference you're probably familiar to if you've ever added sugar to tea or to coffee or to lemonade while you were drinking it. You know how sometimes when you add more of a solid to some liquid, it will keep dissolving, but then at a certain point you just end up with solid, right? No more will dissolve. That's basically the difference. In an unsaturated solution, as I add more to the solution, I can still dissolve more of that solute. In a saturated solution, at the point of saturation, the solution is full. I cannot dissolve any more solute. So an unsaturated solution is a solution that still has room for more solute to dissolve. If you're adding sugar to your coffee, you still have room to add more sugar. In a saturated solution, the solution is full. No more solute can dissolve. If you add any more, you're just going to end up with solid at the bottom.
Quick visual to help you see what I mean by saturated versus unsaturated. So if I have some water and I drop in sodium chloride, NaCl, as the NaCl dissolves, it dissolves because water molecules surround the individual particles, the ions that make up NaCl, and physically pull them apart. That's what happens when a solid dissolves. The solution is saturated if all of the available solvent, in this case water particles, are busy and cannot come and break up any more of added solute. Now, if I were to add some solute, some NaCl, have it dissolve, and still have some water molecules that were left over and available to dissolve more salt, so this would be unsaturated. I still have water molecules that can do more dissolving.
The final term we want to think about is solubility. Solubility describes the amount, often a mass, so the amount in grams, of a substance that can be dissolved in a given amount of solvent before the solvent becomes saturated, or before the solution becomes saturated. So the most common way to think about solubility for us is looking at table G on our reference table. It's showing a series of solubility curves. Now, a solubility curve shows the solubility of various substances at a constant pressure as a function of temperature. So on the y-axis, we see how many grams of each substance can be fully dissolved in 100 grams of water at different temperatures. At the y-axis point, if you follow the curve for each substance, that's telling you the number of grams that can dissolve in 100 grams of water to make the solution saturated. So in other words, to know how many grams of a substance should be dissolved in 100 grams of water to make a saturated solution of a particular temperature, we use the solubility curve. I want to think briefly about the impact of temperature on solubility, because for a substance to dissolve in water specifically, the individual particles that make up that substance must be able to be surrounded by water molecules, kind of like how you saw in the demonstration I just did where I was moving particle models around. I need to be able to surround or solvate the solute particles with the solvent. And so in order to make particles of a substance surrounded by water molecules, I'm going to need to think about a different strategy if I'm trying to dissolve a solid compared to if I'm trying to dissolve a liquid. Now, if I'm trying to dissolve a solid, my goal is to separate the individual solid particles that make up that solid, because I have to be able to allow water molecules to get in and surround each individual particle. And so I need to think about how to get those particles apart from each other before I can get the water molecules in there. This means that increasing the temperature, which increases the speed or the average kinetic energy of the particles, should increase the solubility of solids, because if the particles are moving faster, they should be able to separate from each other faster. The water molecules can come and bring away some of the solid particles faster, and the whole process can happen faster. So solids have a solubility that increases in general as the temperature increases. Gases can also dissolve. Think about how soda is made. A machine called a soda stream can put carbon dioxide gas into a solution of water, forcing carbon dioxide gas to be dissolved into water. It does this by forcing carbon dioxide into the bottle and increasing the pressure greatly in the bottle. As you can see, this leads to carbon dioxide dissolving into the water, though when we remove the bottle from that high pressure chamber, we see some of the gas comes out of solution. That's why we see bubbles in soda. As the pressure is released, some of that gas is no longer dissolved and emerges as a bubble. There's still some gas remaining, which is why we can taste carbonated beverages, that little fizzy bit that we taste. So we experience gases dissolved in water every time we are drinking soda, but there are also tons of gases dissolved in our water all the time, as well as in the ocean water. But the thing is, gases do not behave the same way as solids when they dissolve, because gases are already moving really, really quickly. They're already moving much faster than water molecules are. And so in order to allow water molecules to come and surround the individual gas particles, the gas particles actually need to slow down. This means that decreasing the temperature increases the solubility of gases. It causes more gas particles to move more slowly, which increases their ability to allow water molecules to come in and surround them. This is why soda will stay fizzy in the fridge longer than it will on the counter. Now, let's think about the impact of pressure on the solubility of gases. Remember, pressure is the number of collisions that are occurring between gas particles and the walls of their container. Increasing the pressure of a system increases the solubility of a gas, because it increases the number of collisions that are occurring between the gas particles and the surface of the liquid, which makes it more likely for the gas particles to go into the solution. In the simulation pictured, the hand squeezing the bottle represents increasing the pressure. Let's check back in on our learning goals, make sure we feel comfortable defining these key terms around solutions, thinking about the effect of temperature on solids versus gases. Remember, increasing the temperature increases the solubility of solids, but decreases the solubility of gases. Thinking about pressure and using a solubility curve like table G to make inferences about different substances. For more practice with that third learning goal, check out part 2 of this video lesson. Awesome job today.